There is a tiny region of the night sky that appears almost completely empty from Earth. No bright stars dominate it. No glowing nebula stands out. No obvious galaxy catches the eye. At first glance, it seems like nothing more than a patch of darkness. But decades ago, Hubble aimed directly at that emptiness and discovered something extraordinary. The darkness was never truly empty. Hidden inside that tiny patch were thousands of galaxies, each containing enormous populations of stars and carrying light that had traveled across billions of years of cosmic history. The Hubble Deep Fields became some of the most powerful images ever produced by an astronomical observatory because they changed the way humanity thought about the universe. A place that looked empty from Earth turned out to be overflowing with galaxies, ancient light, distant worlds, and structures far beyond what human eyes could see. Now, the James Webb Space Telescope has returned to this legendary region of the sky. And once again, the darkness is revealing secrets. After an enormous observing campaign, Webb detected faint sources that were difficult or impossible for Hubble to see clearly. Hidden red galaxies became visible. Extremely distant objects emerged from the background. Structures buried in infrared light began to appear, giving astronomers another opportunity to study how galaxies were born, grew, and transformed throughout cosmic history. This was more than another deep space photograph. It was a second look at one of astronomy's most famous windows into the universe. And the longer Webb stared, the less empty the darkness became. The Hubble Ultra Deep Field was created from more than a decade of observations and became one of the defining images in modern astronomy. Astronomers pointed Hubble toward an incredibly small section of sky and simply gathered light for as long as possible. The concept sounded almost ridiculously simple. Look at a place where nothing obvious can be seen. Then wait. Collect the faintest photons possible. And see what appears. What appeared changed everything. The darkness was filled with galaxies. Not a handful. Not a few hundred. Thousands of them. Spiral galaxies, elliptical systems, tiny reddish points, distorted structures, and extremely distant sources appeared across the image. Some of the light came from a universe that looked dramatically different from the one surrounding Earth today. It was almost as if someone had opened a tiny window in the night and discovered another universe behind it. What made the discovery even more remarkable was the size of the field itself. The region observed is incredibly small compared with the entire sky. It is far smaller than the apparent disk of the full moon. Yet inside that tiny area, Hubble detected thousands of objects, most of which were galaxies. The message was impossible to ignore. The universe was not simply enormous. It was packed with structure. Whenever astronomers looked deeper, more galaxies appeared. But Hubble had limitations. Its instruments were extraordinarily sensitive, yet some of the oldest, faintest, dustiest, and most distant galaxies remained difficult to study. As the universe expands, light traveling across cosmic distances becomes stretched toward longer wavelengths. Some distant galaxies also contain thick clouds of dust that hide their stars and star-forming regions. To Hubble, many of these objects remained barely visible or completely hidden. So a question remained. What else was buried beneath the darkness? That is where the James Webb Space Telescope changed the experiment. Webb was designed with infrared astronomy at the center of its mission. Infrared wavelengths allow astronomers to detect some of the light from extremely distant galaxies after cosmic expansion has shifted that light away from the wavelengths where Hubble is most effective. It also gives scientists another way to look through dusty regions where visible light can struggle. For deep field observations, this is incredibly important. The farther away a galaxy is, the more its light can be shifted toward infrared wavelengths. Webb can therefore explore a portion of the universe that looks very different from the one revealed by visible light observations. During its observations of the deep field, Webb used instruments capable of gathering near-infrared and mid-infrared information. Together, these measurements opened another layer of the same cosmic landscape. And the observing time mattered. Deep field astronomy is fundamentally a fight against faintness. The longer a telescope collects light from the same location, the better its chances of detecting extremely dim sources. Objects that disappear into the noise during a short observation can gradually emerge after many hours of exposure. And when Webb's observations were compared with earlier Hubble imagery, the difference became striking. Regions that appeared almost empty in the older view contained additional sources in Webb's data. Some faint objects became easier to distinguish. Some tiny structures became more apparent. And the background itself seemed to fill with additional points of light. Webb's larger primary mirror gives it a major advantage in collecting light. Hubble's mirror is about 2.4 meters across, while Webb's spans about 6.5 meters. That larger collecting area allows Webb to gather substantially more photons, especially from extremely faint sources. But the telescope's advantage is not simply its size. Its infrared vision is equally important. Some distant galaxies are difficult to detect because their light has been stretched by the expansion of the universe. Others are buried behind enormous amounts of dust. In visible wavelengths, these galaxies may appear extremely faint. In infrared observations, they can begin to emerge. Among the most interesting sources are the galaxies that appear especially red. A red appearance in a deep infrared image can have several possible explanations. The galaxy could be extremely distant, causing its light to shift toward longer wavelengths. It could be heavily obscured by dust and contain intense star formation hidden behind that material. It could host an active galactic nucleus powered by a growing supermassive black hole. Or it could contain an older population of stars that formed surprisingly early in the history of the universe. Each possibility carries information about cosmic evolution. Galaxies do not appear in their final form instantly. They begin with gas, gravity, dark matter, turbulence, and the first generations of stars. Over enormous periods of time, galaxies merge, grow disks and bulges, form new generations of stars, feed central black holes, and recycle material through repeated cycles of stellar birth and death. Understanding that process requires something more than seeing galaxies today. Astronomers need to see them at different stages of their history.